Yeah, thanks, guys. Thanks.
Right, so our next panel is titled From Surviving to Thriving in Space, Making Life Sciences a Priority. Looking forward toward the future of long-term space habitation, this panel seeks to address the factors and challenges that we will face in that process. I will momentarily be turning over the floor to Dr. Heath Mills, Chief Scientific Officer at Rhodium Scientific, who will be moderating this panel and will be introducing his panelists.
Thank you all for being here today. And we have the great opportunity to follow Jeffrey Mamber, so wish us luck. But I have a great set of panelists here. Please come join us on stage to hopefully fill this gap between the last talk and lunch. So let's have a seat. Let's take a seat. Let's have an inspiring conversation about a very interesting topic. For the last 60, 70 years, humans have survived in space. They have shown that we can go to space. We can go to space for extended lengths of time, from very short missions, short sorties, to longer habitation of up to a year and a little bit longer in some cases. But in many ways, what we were looking at were ways of surviving. Now, as we're going forward, and especially as we're looking at going forward and going beyond Earth, as we are here today for, is let's go from surviving to thriving. And there is a big difference in that. A lot of us survive air travel. We'd much rather thrive in air travel. There are better ways of getting from point A to point B. But how do we get to those points? So my name is Heath Mills. I am the Chief Scientific Officer for Rhodium Scientific. And as Olivia presented our company very well earlier, I'm going to talk more about, and I'm going to have the panelists introduce themselves in a second, but I am coming at this from a scientist perspective. I am a molecular microbiologist, a molecular microbial ecologist, extreme environment microbiologist. My card is very long in different ways and different names, but this talk will be a science talk. And therefore, in the lines of a Chevy Chase movie a very long time ago, doctor, 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 we're introduced, which is good. But thank you for getting that reference. But please, if y'all would, to start off with, if y'all would do a quick introduction, please let them know the amazing things that you have done and the reason why you're here on the panel today. So, Jenn?
Hi, Jenn Fogarty, currently Chief Scientist at the Translational Institute for Space Health at Baylor College of Medicine. That is a cooperative agreement that's funded by the NASA Human Research Program with the charter of doing very innovative and disruptive life sciences research to address the human system risks that we've identified and also fill the gaps. You know, we have the known unknowns, which is pretty much where the risks sit, and we have the unknown unknowns. How do we continue to discover and interpret that information so we can be better prepared to not only survive but thrive? And I'll just add that as this discussion goes on, even the intros, that surviving and thriving are both very contextual. So we have to think about what we're asking, where we're asking people to be, and what we're asking them to do to interpret what those things are and what success is.
I'm Angie Bukley. I'm with the Aerospace Corporation, and I am an engineer, so I'm probably, I'm the only engineer on the panel, but I'm currently working in the Center for Space Policy and Strategy at the Aerospace Corporation, and I have a very strong interest in human spaceflight research to support human spaceflight, and I'm very excited just to see all of the things that are unfolding now. And we have gone from surviving to working in space. We're pretty good at working in space, but I think that next step to thriving is a really important step. And I think some of the things we're going to discuss on this panel today will help us understand the challenges and the opportunities we have to get us there. So very exciting times.
I'm Jeff Davis, physician. Worked for NASA in the 80s, then American Airlines, and was at the University of Texas Medical Branch where we got the aerospace medicine residency training program going, and then came back to NASA in 2001. And when I finished up, I was the Director of Human Health and Performance at the NASA Johnson Space Center, so very interested in this panel. And we did a lot of work in the mid-2000s to put the human system risks together to better understand and prioritize the things we were worried about for long-duration spaceflight. And I think that's had a nice evolution over the last about 15 years, so thanks.
Excellent, excellent. Thank y'all for those introductions, and I'm very honored to be with such amazing talent that has a long history of understanding what it was like to and what it is like to operate and, as Jennifer said, work in space and to move this forward. But I want to step through the discussion today from going to the fundamental biology side to more of the functional side with the astronauts and their health and how they progress, to then to the logistics and even to the flight dynamics. And so we're going to progress the discussion through this in that order. But so therefore, to start off with, I would like for y'all to discuss and talk about the differential or the need for, yes, there's a lot of talk about applied research and applied biology and functional going and solving specific problems, but also the fundamental side. Are we ready to move past fundamental? Do we still need a very big and good understanding of the fundamental science, the fundamental ways that biology responds and adapts to the space environment? And so with that, I know, Jennifer, we were talking a little bit on the side and before about that topic. What is your thought between the fundamental versus applied research and where we should work and progress?
Okay, Heath, I appreciate that setup.
You like that one?
Yeah, that's like a softball.
Yeah.
Or good luck. Yeah, so actually that's the space I sit in with what I'm asked to do. Strategically plan a scientific portfolio that has a variety of elements that are addressing the fundamental need to deal with near-term problems, things we know that are happening with crew members today, the problems that have happened in the past, the fundamental kind of vulnerabilities of being a human when put into a stressful environment may lead to outcomes we don't desire that create risks for not only the individual, but for the mission, the station, whatever it happens to be. And that is where you get the concept of applied work. What are we learning about humans on Earth? How does biology work? What medicine can be brought to bear? And then we can flybridize it. You know, can we take technology and the methodology, the detection capability, the treatment capability, and make it doable on a space station? The parallel is, can I also put it out in remote Earth, you know, for the same purposes? So there's many parallels there. The other side is continuing to invest in the things we didn't know we needed to know. The fundamental biology of how life adapts to and where that adaptation takes any life form when you put it in a very stressful environment that's not quite the one that we live with today. What kind of changes will that lead toward that give us the prediction ability to say, there were medical conditions we could have never anticipated because we really don't manage them here on Earth, but we saw this coming because we had a bridge from a fundamental understanding to what it meant when you put it in the context of a holistic human. And that is actually a huge struggle. You see that struggle going on in medicine today over probably the arc of the history of medicine, but particularly because we have a couple of things that are very poignant in terms of we can see, literally and figuratively, more than we've ever been able to see before, submolecular level changes. The problem is, how do you interpret a change you can measure? What is the context of the change? And is that one change really predictive of a whole organism, you know, having a negative outcome? We're not sure. So, and you also have the public nature of science, the media-driven process of watching science unfold in front of your eyes. It was so typified during the pandemic when on a daily basis you could get an update of what they were finding in any one laboratory, and everyone was aghast because we didn't know it yesterday, and that might change what we did tactically tomorrow. But that is the process of learning. It's messy and it's uncertain, and it can be filled with amazing discoveries, and you have to be ready to capitalize on those. But it's mostly filled with, I would say, the concept of failure. It's filled with times that we don't understand what we're seeing. It's filled with times we can't interpret what we're doing, and it has to sit and wait for its moment to be put in connection with another piece of information to be seen of value. And that is like this large scientific machine that requires, the national academies. It requires, expert groups to come together. It requires the peer review process and publication and that churn of moving in through information through the process of maturation so we can figure out what to do with it. Right now, I think we have a very disparate approach. There's lots of shots on goal. There's a lot of single point solutions out there because there's this need to start to fill this void of information. A colleague of mine said it perfectly a couple weeks ago, that as much data as we're able to generate, we're actually incredibly data poor. And that is because it is very hard to measure things in space flight the way we do here on Earth. So I think the next stage of this conversation is to actually have to reimagine how we have to implement for an extreme environment like space and not just try to transport what we do on Earth up there. You have to, and in my case, I'll start off with an example and then hand the microphone down the line for that question, was if you think about one of our groups very much needs to be able to image the brain. And immediately, if most of us in this room have access to pretty good healthcare, you're familiar with an MRI or a CT scanner, and that would be something that you would probably be, put into to get a good image of your brain. That is not a realistic solution for spaceflight. It may not even actually be the best solution for Earth, but it's the one we know, we trust, and we're familiar with. But EEG, electroencephalography, measuring the functional representation of the brain is actually an image of the brain. It's not a photographic or physical representation of the anatomy, but it is actually how your brain works. Why is that not considered imaging the brain? And so trying to flip the script a little bit on how we characterize tools that we use today for a certain utilization case and have to reapply them. And it will have to do a lot of work with evidence base of how we interpret this, something like an EEG signal. But that's work worth doing because it is light, it is lean, it is resource, minimal. And I think it's going to deliver more information because while we could find something anatomical wrong with your brain, if it doesn't have a functional effect, is it worth knowing about? Is it something worth interceding on? So there are other areas too that I think really are going to push the limits on having to change the way we do healthcare and life science in space that will not just be the recapitulation of Earth methodology.
So I'm not sure how much I can add to what you just said, but, but thanks for that. No, I think that we still have a lot of work to do. I know we still have a lot to learn, and Jen's just explained, just some of the things that we have to do. I think that we're coming into a very exciting time with more commercial spaceflight, more opportunities to do experiments, more opportunities to learn, not just from people, but also experiments on plants, other animals, and so forth, and try to understand those fundamentals that are going on. One of my professors a long time ago said something to me that has stuck, and it's everything in space is trying to kill you, and it is. It's trying to kill you or wreck your spacecraft or something like that. So I think it's really, really important that we better understand and adapt how we do things in space, especially from the medical standpoint, because you're right, putting an MRI on a spacecraft is probably not practical, but there are other tools that we can use to garner information to help us learn more about what's going on. And to me, the most exciting thing is soon learning what's going on with people who are not, perfect physical specimens, just regular people. We've not flown just, we've flown a handful of space tourists, but we've still got a lot to learn about, how people with different maladies would respond to the space environment, microgravity, things like that. So I think that's about all I can add.
So Jeff, before you start, I'm gonna throw a curveball to you. So it's not gonna be easy on you on this, because we've had a good discussion about the fundamental side, and I want you to talk specifically about our understanding of the gravitational field, of going from 0 to 1, and how our understanding and the fundamental understanding of how gravity impacts biology and how we don't know if it's a continuum versus a threshold, How do we address that going forward as a fundamental understanding moving to an applied side? So I think you got a great perspective on that.
And I was just going to add, first to the previous comments, that there's a linkage, obviously, between fundamental and applied. And a lot of space medicine over the last 60 years has been, I would say, observational. Data was collected, patterns emerged, and we're still in that environment today where something new comes up, and we have to go back and ask not only what do we do about this, fly different equipment, fly different medications, but what's the underlying cause, if we can determine that. And that's an ongoing research endeavor right now. One other thing I would mention too, with even the applied research, one of the challenges we always had as new programs were coming online was the timing. And so if you had a limited amount of time, 4 or 5 years perhaps, before requirements needed to be specified, pick something, the medical kit itself or environmental life support, it bracketed the amount of research you could do. And so the way I like to think of it back with that was come up with the better answer you can by that time, maybe not the best answer or the complete answer, but what's the better answer so we can positively impact requirements for human health and performance on that vehicle. Going back to the question about gravity, I think that's really an interesting problem because we don't know at this point if what the pattern or the line would look like, if you will, in a biological system from microgravity to 1/6 to 1/3 to 1 G, and that would be really interesting to know. There was some ground-based research that was going on 15 plus years ago using bed rest and then trying to simulate 1/6 G and 1/3 G. And that data would have been interesting to try to understand could we start defining a potential curve? The reason as a practitioner I would be interested in that is, does it help or augment the countermeasures that you're specifying for a particular flight? And if so, how much? Is 1/3 G enough to trick the body, if you will, in certain subsystems to maintain health or perhaps reduce the amount of involvement you have with countermeasures? So what would 1/3 G perhaps reduce the amount of exercise time? We don't know the answer to those questions, but they're all linked together. They would be really important, I think, to know.
Right, and I think that you can see, and I really wanted to do a high-level question to begin with, to really point a finger at we have a lot more to know. There's been a lot of amazing research that's been done in space of the human system, but also in the other biological systems that are there to support those human systems. And so as we're going forward, we now have to start considering more of a detailed, directed understanding, research-based approach of how biological systems adapt to and now start to thrive within this environment. And Angie, you brought up the point there of we are experiencing a change in who is now going to space. Before, it was highly selected, highly trained individuals that were very, very adapted to a stressed environment, a pressure environment, an environment that was extremely rigorous, both mentally and physically. And now we're changing to us. But we're changing to a general population, and we're trying to literally open the doors to new vehicles and new ways of being in space for the common person, which means now, you said that we have different people now going to space and different adaptation. What do you see as those challenges are going to be presented to the different companies, the different CLDs, the different providers going to space and eventually to the moon and beyond? How do we address thriving in space for the common people? What type of challenges do you see as that we presented?
Well, there are a lot of challenges for that because everybody's different. And the people who will be going as space tourists, they're not going to be, trained fighter pilots. They're not going to be selected in to be part of the crew. So I think it's going to be challenging to better understand how the space environment affects those people. And I think it's a really exciting time. And I think it's great that we're trying to open it up. Like right now, basically I don't know what the requirements are for the suborbital flights. I think George could tell us, but at any rate, I think, it's done right now with waivers, So you sign a bunch of papers and say, yeah, this is dangerous. But it's also, I think it's very exciting times that we can open this up and learn more, because now, we don't know how microgravity affects people with certain conditions. And like you said, we don't know the gravity prescription. We don't know what that level of gravity is that would be a sufficient countermeasure, to help prevent some of the things that happen to the human body in microgravity. So there was recently an experiment done. I'm going to jump back to the gravity question real quick, and it's relevant because it was done with a population of test subjects that weren't the fighter pilot type. They were selected, but there was a parabolic flight mission back in June where we flew 3 different gravity levels. We flew 0.25 G, 0.5 G, and 0.75 G. And that was actually a NASA experiment that flew, and I don't know that any of the results have been published because that was just in June, but there are some ways we can start to learn a little bit about what we need to do in terms of gravitational levels. But yeah, I'm just, it's just really exciting to think about, having differently abled people be able to go to space, older people, and some of these people we're talking about aren't going to be going there to work, but eventually we will be sending people to space to work.
Right.
And so we have to understand what the long-term implications of that are, and how do we take care of those people and make sure that they can perform the function that they're out there to do. So I think we've got a lot of, still a lot to learn, but I think we're on the right track to get there.
Excellent, excellent. Jennifer, if you want to add to that about the collection of data that now we'll start to learn from these different individuals going up. And so if you would provide a little bit of perspective there.
Sure. Yeah, I think that was, very insightful in terms of the opportunities with people who are differently abled or come from a different health status. But that does put the priority on requesting that they participate in data collection. And that actually recently came out. We held a bioethics workshop in December to have these poignant discussions. There's this huge opportunity, and with great power comes great responsibility, to contribute to the knowledge base. Like, if you are someone who has a compromised health compared to the population we're used to, and I do want to bust one myth, and I see a colleague in the back that's going to appreciate this. Like, astronauts do not have perfect health. No such thing, right? Health is on a continuum. But we do have people, and I would say probably most of the people in this room qualify as having a healthy worker effect, for a couple of reasons. You're probably well educated. You probably have the socioeconomic resources to get health care. You have the freedom to have transportation to find it. So you probably would find yourselves in a position to have better health outcomes than the average population itself. When you start talking about these opportunities of flying people who for various reasons may not have less perfect health, you start to have to ask questions about reserve and resilience and biologically what that means. Because when we talk about thriving, that talks a lot about the ability's plasticity to respond to change and then recover from that response. And when you are compromised by a health ailment like a chronic condition, your reserve will be degraded. It is very hard to quantify right now what that means. We're all working really hard. I'm trying to build a dashboard for each individual of key metrics that you should follow. And you're doing it. Like, I got a Garmin on. I know there's Fitbits in here. I know there's Apple Watches in here. It is chock full of data. And we want to use simple tools like that to collect this data. We know it needs to be unobtrusive, non-invasive to get it from people. But it's key. If someone has a pacemaker defibrillator and they have existing coronary disease or, the underlying condition that requires that hardware, can they have reserve and resilience? And how long does that last? Do we start to get a window of time where someone under those circumstances could thrive in a spaceflight environment? And then the question is, safety has come up a lot this morning. when has it become unsafe for them to be there for their own purposes, but for the rest of the crew, for the mission? Like there's lots of connections there that we have to be at least transparent about. I get people can sign waivers. People will sign waivers for anything until they're in it, and then all of a sudden, like, I changed my mind. I don't like it so much, right? And you're like, well, you know, your free will suddenly disappears mid-space flight of what you signed up for. So now we can get into the psychology, and then I'll tip that off to Jeff, because he's... But I think these things are opportunities, and most of the people we've engaged with, Trish has a particular program with commercial space flight to try to collect this data and make a compelling case of why it's so important, why every data point matters, because again, that metadata, that contextual data of who you are and how you respond to those stressors is so informative, and it'll only become a deeper and more useful database the more we populate it with variety and diversity. On the cellular level, what's super interesting, what's coming out, and this goes back to the fundamental, why you need fundamental research, because we can study at a single cell level, whether it be a microbe or a human cell or a yeast, that there are changes in the cytoskeleton. And for a long time, there's many things I'm sure you've heard in biology. People are like, that doesn't matter. You heard the phrase junk DNA. I think our egos have taken a big hit, and there is no such thing as junk DNA. We just didn't understand. It's like UFOs. It's only unidentifiable. It's not, you know, you got to pay attention to what you don't know about it before you dismiss it. And in the case of the cytoskeleton, it is actually how the cell, it is a major transport route, right? Things are not free-floating in your cells, just bumping into each other accidentally and making good outcomes. They are directed down different paths within every cell of your body to do a job. Your body is the most efficient machine you will find, you know, to study. But when it gets disrupted, then we say, what does that mean? Now, I think, going back to the idea of you can't avoid all change, but again, you need deep data to understand what does that change mean and use that information to then predict where it's taking you. So, Jeff.
Yes, sir.
I just wanted to add to, you know, it's a matter of perspective also about surviving and thriving in space. So when I first started, we flew 5-day missions. And I don't think at that time, anyone envisioned we would be flying 1-year missions, and certainly not 371 days. Frank Rubio just came back. So over the last, you know, number of years, the amount of data collected, the types of illnesses and injuries we've seen have evolved. We've taken I think a very balanced risk management approach to that, and standards have evolved. So from the earliest days, and so a lot of learning has taken place. And I think with the addition of commercial space, that will only continue, because now we're going to be seeing cohorts and populations with different illnesses, different medication regimens. And we need to know how all that behaves in space, if you will, over shorter and longer duration missions. My guess is we'll learn kind of in the same format, where shorter missions will occur first. I think in that case, that's much easier to manage. And you'll learn how to evolve to longer and longer missions for folks with different issues that can fly safely in space.
And that's an excellent point on this, is that we will be flying and are flying individuals over different durations. But one thing that is common is that, and maybe for not the best reasons for operational awareness on orbit, we kind of expect when the hatch opens that you're supposed to go to work. And you're forgetting the fact that you're in a very foreign environment. Everything up and down doesn't exist. You hit your head, you do kind of crazy things, you're a little bit inflated and bloated, and it's weird. And when we go out onto the ocean, we go out and see, we know that, hey, do you get motion sick? Here, take Dramamine. It's a great countermeasure. Now you can go out to sea and have a fun time. When we start putting different individuals on orbit, we're looking at different maladies. How do we find those countermeasures? What should be these countermeasures? How do we go and start addressing these so that the tourist doesn't spend the first 4 days completely out of their mind, can't do anything, and have a horrible experience, or the worker is able to start working? And so as we have these commercial stations, this may be a very valid point. Are we there yet? Do we know where these countermeasures are going to come from? What are your thoughts on developing that magical pill that allows you to go to space and be completely functional. Is there one, or is there what do we do? Jeff, you want to start with that one?
I don't think there's a magical pill yet.
Sorry,
But
that's it.
we have learned a lot, and in some cases, we've moved from prophylaxis of a problem to treating a problem, say with motion sickness on orbit. And I think we'll also gain a lot by terrestrial medicine for folks who are flying with a lot of different maladies. So if they're on a stable, functional regimen, and there's no reason for us to think it would behave any differently in spaceflight, then that person could fly, and we will gain additional knowledge from that. But in the main, I'd say once you get past the first few days, that we're doing pretty well, I think, with thriving in space for long, very long duration missions at this point. And I think that will just continue. That knowledge base will continue to evolve from commercial space, and maybe that will lead to the magic pill someday. But
So one of the magic pills from a prior boss of mine was the tincture of time. So for some of the adaptive responses, you cannot speed them up, and actually countermeasuring them slows the adaptation process down. So it's a trade-off to make someone feel slightly better, but their adaptation process may take some percent longer. The other thing that we've been challenged with human spaceflight, and I say that as opposed to non-human spaceflight, because we are complex, we throw a lot at the engineers in terms of what we're going to demand and how much can we accept in terms of, compromise there. But there is a purpose to interact with your new environment with little to no mitigation so that you learn how to adapt. And that is where 24 to 48 hours, it is remarkable, even for people who are differently abled, how quickly that, we think of it quick. If someone wants to adapt on the order of minutes and hours, that's a tough way to go. There are people who naturally do it. We've talked, and Jeff and I have lots of conversations in the past about watching the crew members return. The best returns to watch for long duration spaceflight are the ISS returns in Kazakhstan. And just the look as the cameras pan between the three chairs and the shades of gray or green, and then who the medical crew is cloistered around. But the extremes matter. Those are huge from a scientist standpoint. You get kind of greedy because these are people who are typifying the two ends of the spectrum. Who are you, and why did you end up that way? Was it something about that day where you're not properly dehydrated, or was there a fundamental genomic reason why you weren't prepared for this quick change in environment? Because I need to know both of them so I can kind of meet in the middle. And going back to the idea of using pharmaceuticals as countermeasures, one of the things that immediately makes us more precise is the advent of pharmacogenomics. There are many drugs that are lined up with genetic pathways that then describe how you work biochemically, that the FDA even recognizes, and we can map them. So I don't have to guess, what works for you, and I could probably get much better closer to the dose so you get less side effect. So off the bat, that's a reason, knowledge is power. We can use science that way to cut down risk and be more efficient. In other cases, that those relationships aren't known or don't quite exist that way, and you're gonna have to do a little trial and error. But the expectation is that all of these people are going to give us a better way to narrow in when we have to use pharmaceuticals, when we can use time, when you would use a physical, manipulation of someone. Bracelets were a really great idea when people went on orbit. It's very simple, like the space pencil instead of the space pen concept. So I think there's a lot of information to analyze, reuse in the contextual case of what mission are you on, what are your pre-existing vulnerabilities versus your strengths, and then how do we figure out what combination of tools are going to help you have the best experience and be the most functional.
Yeah, and you raised a good point, talking about the landings in Kazakhstan, and as the cameras pan across, it gives you something to think about when a crew member or a crew has spent a lot of time in space going to Mars. Are they going to be able to egress their vehicle on their own? I mean, it's 0.38 G, excuse me, but still, you're going from a microgravity environment to a not microgravity environment, and you've been in a microgravity environment for a while. So I think, learning things like how we can help people get through that quicker, what might the crew be doing in the days leading up to landing, and learning how to deal with the G transitions. And I think that's what triggers a lot of the space motion sickness. And I know that's what triggers it on parabolic flights, going from 2Gs to 0G all of a sudden, and it's a pretty quick transition, as I understand it, going into space. So, we have to understand how to deal with that. Everybody's different, but I think it's just really important that we keep pursuing that and find out, what is that? Is there a magic pill, or is there a magic regime that we can have the crew execute, even before they go? I know there's a lot of adaptation training. People riding centrifuges to get an idea about the G levels. The more we have people doing that, the more we're going to learn, the more data we're going to have, and eventually we're going to get there where we can confidently send people into space to have fun or to do a job.
Absolutely. Jeff, you want to add something?
Just wanted to add one quick thing. So as we do better with personalized medicine, as the years go by, that we'll be able to give people not only perhaps better treatments, but better knowledge and information, and that is pretty powerful in getting someone ready for spaceflight. So if they know what to expect for themselves, him or herself, going into flight, that would be very important as well.
Go ahead, Jen.
Yeah, to that point, expectations matter. So the connection, the mind-body connection, by having experiences like suborbital flights, zero-G flights on centrifuges, helps you learn how your body responds, which is why the undercurrent of why we're the original and still a predominant part of the astronaut corps, military jet pilots, people who jump out of planes or fly planes in unorthodox, accelerations and directions. It was to quote Dr. Mike Barrett, astronaut physician, is get comfortable with being uncomfortable. The anticipatory effect of fearing something, the sympathetic drive that gets turned on, sets off a cascade of events which can very much not be your friend. And you know that about managing your own stress, right? This is a fight or flight response. It's going to change your blood pressure, your heart rate, your physiology, to the extent of you may be less resilient in those moments, and there's details in heart rate variability that get us there. So that is an incredible just countermeasure in and of itself. Those experiences before you go, so you know even how your own body is going to manage it, and you can manage yourself better, are really important. So I think that's been something that kind of is overlooked, because it's not the magic pill, Heath. Not happening.
No magic pill. Well, you can quote us on that one. So I want to throw out, before we go to questions, and I want to have enough time for the audience to ask some questions here, but I do want to throw in one other slightly different topic, because we're talking about the humans. We're talking about the human experience, the physiology of the human side. We also talk about now going forward, out past Leo to lunar and to Mars. We always talk about the space vehicle, whatever it may look like, as being an austere environment. Jeffrey Mamber just put up Hilton. That's not like austere environment. And we all applauded that it would look different. The environment would be different. So now, when you start talking about supplying these missions, keeping that environment to now a thriving environment, do you see us being able to, and how do we use life science? How do we use some of these experiments that we're doing now? Maybe it's through biomanufacturing or through different ECLIS systems and ways of looking at ECLIS. How do we help support the humans through other life science experiments? What else is needed to transition that austere environment to a thriving environment where supply chains may not be as much of an issue and we can maintain our presence going forward? And so I'm not sure if maybe, Jeff, if you want to jump in there first on that one.
Well, in terms of even longer duration missions or off planet to Mars, that a couple of areas that will need a lot of attention, if you're depending on who you're taking into space, would be the pharmacology, the pharmacy, and food systems, which beg all the questions you're talking about resupply and pre-positioning and all that. So, for a Mars mission that may be 32 months long with pre-positioning, some of the unanswered questions at this point: will drugs be available for that 5-year period? Will the bioavailability be sufficient on the pharmacy side? On the food side, and Jenn talked about the psychology. Food's important, especially for long missions like that, and it's social, and having a appropriate variety and change that's available would be very important as well. So beyond the physiology, which I think starting to do quite well with, that some of those supply issues are going to need some real priorities.
And I think some of the challenges are going to be with the environmental control and life support system for sure. We're a ways away from having a closed loop ECLS design. So to be self-sufficient, we're going to have to figure out how to close that loop so that we can produce the food we need or the nutrition that we need. It may not at first look like what we're used to. We're used to green vegetables and all these nice, wonderful things that we can eat here. But when you go to space, or if you're on a long duration mission, like Jenn said, you have to set expectations. At first, it probably will be fairly austere. It'll probably be a lot of freeze-dried food and things like that until we get to the point where we can actually produce what we need in a closed-loop fashion. And we are a ways away from that. So still a lot to learn on that front. One of the things that's always astounded me, I've worked on a lot of different space systems, a lot of different spacecraft, robotic missions, human missions. Just the mass of the ECLS system it just adds so much cost to the mission because mass is money because you got to get it up there, and we have to take care. We've got to be able to breathe. We have to have water. We have to handle waste. We have to be able to put out fires. So there's a lot to think about when you're talking about the ECLS systems. So we still have, like I said, a lot to learn on that front, but we're making steps, incremental steps. The National Academies just came out with their Biological and Physical Sciences Decadal Survey, which I had the privilege to work on a little bit. But one of the things that we'll be looking at there, that NASA will be looking at, is food production. So that really is important. But again, I think setting expectations at least for the initial explorers that'll be making those first trips out. It's not going to be the Hilton. Maybe it's better than what we have now. But I hope as we think about how to design the interiors of these spacecraft, we also think about the environments. The microgravity is different, so you don't use your legs. You're going to have handholds. You're going to have ways for people to move themselves. If you got that, like the picture that Jeff showed earlier that looked like a Hilton hotel room, if you're in microgravity, how do you get from your bed over to the to the restroom? You got to think about practical things like how do you move around in microgravity. So lots of design considerations, and that's kind of what gets me excited being on the engineering side of things.
Do not underestimate the habitability, right? Even though, poked fun at it, Hilton's going to need some Velcro. Like, it's not, that pillow isn't going to stay on that bed by itself. So companies coming into this, learning what it really means to live and work in 3 dimensions and what happens to the body is not trivial. So, there's a big concern. I've worked with a couple companies, you really got to generate those requirements descriptively. What are you trying to achieve here, and what are you up against in terms of it doesn't function like it does here on Earth? To completely reimagine it. It still could be more luxurious, but there are some fundamentals of spaceflight. Unless you induce all 1G artificial gravity, that's just the nature of it. I think it is a really exciting time to think about using low Earth orbit as the place to test very different systems and reimagine it instead of the vehicle being a machine, that it's an exoplanet. These people are going to need bioregenerative ECLS. You're going to have to think about the human in the cycle, and you're going to need plants and microbes to make all of that happen in that diversity of life, not only to clean the air and clean the water, but provide the biomass. The other thing, when Jeff was talking about pharmacy, is on demand. And I've worked in this space long enough to have seen and argued back about 3D printing a lot. Why? Because 3D printing needs raw materials. Like, where is all this stuff coming from? You know, that you get this active ingredient you got to bring. And my thing is, like, who's going to clean it? Like, every time, like, with a food 3D printer, I'm like, who is cleaning this? This is like a hot mess. Like anyone who's worked with a food processor, and you got to take that thing apart, you find stuff everywhere. Like, not the good stuff, Heath, not the good. This is the biofilm we're trying to avoid. But synthetic biology, engineering biology, as part of a bioregenerative ecosystem, can give you on demand. It can synthesize active ingredients. There are studies, there is stuff going on that is just, talk about disruptive in the best way possible. But that as something where, yes, you may have to, facilitate a medical kit and do some prediction and take some stuff with you, but pretty soon you're not going to have something you need because you couldn't have predicted it, or you don't have enough for everybody. And you got to have a way to send up the code. It's all about the software and the interface requirements. The other element that was mentioned before in terms of this exoplanet is we can make a medical system that is essentially vehicle independent except for power and data transfer. Like using low resource wearable detection and analysis capability, using the software to drive integration and also interpretation can really get us where we need to go, where we're not doing racks anymore. We've got probes for an ultrasound attaching to, a port. The people are actually, their clothes are giving stuff, biomedical data off of them to be able to track them over time, to get that signal of when did change take you away from adaptation and toward a more pathological state. That is really the goal of preventive medicine, and we're not there on Earth. But because of the need for spaceflight, it's going to be the forcing function that makes us have it there first, and then we will be able to bring it back. And there will be a market for it because people will know it's possible. Right now, it's not really possible. We're kind of stuck in this muck and mire.
Exactly. Jeff, real quick.
Sorry, one quick comment. I know you want to get to questions, but one thing that has been done that's been worked on is lighting, and that's important. We are 24-hour individuals, and that can make a huge difference. And when you're designing a vehicle, the questions would be, is it 24/7 operations? Are you going to separate those out from folks who are working there versus folks who are coming as tourists? Because sleep disruption is a huge issue, and you're going to have perhaps these mixed crews. So how are you going to design or separate that vehicle, address the lighting, things like that?
Exactly. And to add to what Jennifer just said, I like how she said send code up. And as a genetics guy, I'm like, yeah, you can send DNA code up, print out the DNA, and enable a biomanufacturing system to now produce a therapeutic. So code can be ones and zeros in computer code, or it could be biological code. And I think transitioning to the life science biological way of thinking can enable a vehicle or a crew to do things that we need them to do without a resupply. So I think going forward on that would be really interesting. But before we break for lunch, we need questions from the audience. So please, if you have any questions, raise your hand up and let's grill the panelists. Let's have fun.
Hey,
back in the corner back there.
I'm gonna take the first question real quick.
Yes, sir.
Fascinating conversation, Dr. Heath and the other doctors. You just touched a little bit on artificial gravity, right? So there's been a lot of discussion about how the body behaves in microgravity and how to mitigate that and so forth. But now, can we talk a little bit more about how do we engineer out and resolve some of these issues? And one of those, particularly about microgravity, I know that we had a lot of discussion about that during our prep calls. So,
I can start with that first. I actually prefer the term fractional gravity. That's just my term because artificial gravity immediately sends the message we're going to spin the vehicle, and that may or may not be true in transit. So first of all, do we know enough about fractional gravity, 1/6, 1/3 g, and the impacts to the human body? Secondly, if you do end up spinning a vehicle, do you stop at 1/3 g on the way to Mars? The sort of counterintuitive comment is if you spun it at 1 g, and now you arrive and you go down to 1/3 G, have you done any good, or have you possibly just reset, the decline that's going to happen in muscle and bone system? So a couple of things to think about.
Yeah, generating fractional gravity on orbit. Coming from the engineering side, yeah, it's challenging, but it is doable. In fact, we had proposed an experiment to actually rotate the shuttle before they had to do the little maneuver when they get to the space station, because the shuttle could have done that. We could have just, seen how the vehicle responded and how the astronauts responded. But I think some way to generate that fractional gravity, especially going to Mars, if you're expected to be fully functional when you get there. And maybe you're right, 1G might be a little bit too much, because then having experienced Mars gravity in a parabolic flight, it's different. It's not horribly different, but when you pick up your feet to walk, your feet come off the floor really quickly because you're used to fighting the 1G. But in all seriousness, it's something we need to look at. I'm very interested, especially with the design I saw from VAST this morning on how they intend to spin the vehicle. If we do generate fractional gravity by spinning a vehicle or spinning a part of the vehicle, we have to be really careful to consider what happens with the Coriolis forces and cross-coupled accelerations. Those can be incredibly provocative and cause extreme discomfort. So lots to think about, lots of design, lots of trades to do there. What's the optimal radius? What's the optimal spin rate? Things like that. Yeah, lots of exciting things to think about.
Well, another area where we're very data poor, to have the biology side weigh in and give a prescription, whether it be short arm, long arm, it's a gradient across the body on short arm. Everything you just said about, the cross coupling and the, people, it does not incentivize people to want to do it when you don't feel well trying over and over again. But we've had a significant amount of starts to work on artificial gravity that has been subsequently canceled and incomplete. We have never amounted to enough data to sit at the table with the engineering side and do the business case of, is this worth doing? Does it mitigate enough of the risks in the human, and how many does it cause? For us to really come to a position of what should we do. We sit at a table and we speculate endlessly, and we kind of leave the table without the ability to go anywhere with it. And I think at some point you need a sustained funded effort to do it and get the data to make it an informed decision forward.
Absolutely. Jeff, you want to add
Just
one more thing?
one more quick comment that there was work done, many years ago with slow rotating rooms, and there is a subset of the population that even when you slow down to 1 to 2 RPMs, that don't tolerate that spin for the Coriolis forces. They still have an issue moving their head in that acceleration environment. So again, there's a lot of design issues to think about. But there is some older data to go look at.
And I think there's a business model case in this as well, because if we have and understand that gravity, is it a gradient or is it a threshold response? It's a very simple biological question. If it is a threshold, where is that threshold? Because if you're preparing to go to the moon, and the moon and zero gravity, microgravity LEO are on the same side of that threshold, then you can get people acclimated, supplies acclimated, biological systems acclimated in low Earth orbit, and then go to the moon. You can do your testing and all of your base rates and analysis and everything in LEO, and then go to the moon. If Mars is on the same side of the threshold as we are, then we're good to go. That's an amazing question to find out and to answer. And from a business perspective, from moving forward, going out, wouldn't you like to know that? Yeah, thank you. I got one vote. That's perfect. But that's where we need to put the fundamental work, and testing on the ISS and doing a low-speed centrifuge there and looking at ways of testing this can answer a huge question business-wise as well as scientifically. I think we had another question back in the back here.
So my question comes from the perspective of another field of research that we can't study directly on Earth, which is injury biomechanics. So I'm wondering if you can speak to the extent that we use animal or computational or any other alternative models to get at some of these questions.
Was injury biomechanics?
For example, we don't shoot living humans to test how Kevlar systems work. Frankly, we shoot pigs, we shoot freshly dead bodies, we do other things to study this.
Yeah, I mean, there are analogs on Earth. I mean, they've been using humans on sleds. I mean, it depends on which example of, I guess, the threat. You know, in the musculoskeletal injury world, there are questions about being unloaded for long periods of time. There's going to be changes to the cartilage that when you suddenly reload it, regardless of the level of G, you know, do we, you know, incur an injury risk to that tissue? So animal models have been useful, but like all models, they're wrong. You know, it has limited extrapolative capability. So, I mean, I think we use a variety of different ways to kind of triangulate our way to a most reasonable answer. And then we do actually have examples of accidents and returns that have resulted in catastrophic injuries and such. Right now, the injury risk on landing, because of the changes to the neck and the spine being offloaded for so long, has of been great interest. So regularly there are studies immediately post-landing, you know, via the more typical, you know, image gathering modalities to study risks. But I think there's been a suggestion of flying different animal types, especially some larger animals. Unfortunately, you're still going to deal with the biomechanics being so different because of, you know, being a quadruped versus bipedal, and where you start from is very different. So they have their challenges, but there are some opportunities there to segue into larger animals.
Real quick, because we got to go to lunch.
Yeah, I was just going to mention, does not exactly answer your question, but the injury models that exist, there was some work done also to try to modify those for future design vehicles based on a deconditioned crew member, because a lot of the injury models, like you were talking about with studies on the Earth, were for folks who are being studied on the Earth. And if you're returning and somewhat deconditioned at different states, how are those injury models perhaps different? And there was some work to try to at least modify or build a bigger range around those standards.
That's where that modeling came in. Yeah, to account for the delta, yeah.
Good. All right. Thank y'all very much. Steve?
Thank you.